So we're scheduled to start in like 2 minutes, but we can start talking about the class, I think. That'll be okay. Who's excited to be here on Wednesday? What's your favorite thing about Wednesday?
Middle of the week, so you're halfway done.
I love that. You're middle of the week. What do they call it? Hump day? Right? You're in the middle of the week. You know what that means? That means you're on top of the week. You have vision down at the things that you didn't do at the beginning of the week that you were supposed to do. And you have the whole rest of the week to finish those things. Right? Middle of the week. I don't know why people give Wednesday a bad time. It's the great song, the Geico commercial song, with the camel walking through the office and singing. You guys know that, right? Sweet. I once did a theme for ME 1800. My theory was that people would be a little bit more awake and more willing to pay attention to the lecture if I showed a cool YouTube video at the beginning of every lecture. Do you think that actually works? I'm not certain it worked. I didn't keep doing it. It was fun, and it was actually fun to find cool YouTube videos. It was fun to find cool YouTube videos that maybe were aligned with the content of the lecture. But yeah, we don't do that anymore. Okay, so we're ready to start M1800, CNC machining, and prototype manufacturing. Somebody tell me, what is CNC machining? Yes. All right, so the CNC stands for computer numeric control. What the heck does that mean? Computer numeric control. Actually, it doesn't matter. It's like it's like one of those terms that, what's another word for it? So back in the day, so I like to call it Etch-a-Sketch machining. Anybody ever use an Etch-a-Sketch? You get the thing with the two knobs and you hold it upside down and shake it to clear it, right? So machining at the beginning was done with Etch-a-Sketches. Well, actually, I guess machining at the beginning was done by like carving, right? The same process of carving. Anybody ever like whittled wood with a knife? Carved something with a knife? That same process of making chips in the wood with your knife is the same process that we do when we do CNC machining, except the knife is harder and it gets pushed with more force when it goes through steel. Does that make sense? Or stainless steel or ceramics. So the machining part of it hasn't changed. And so back in the day when we started doing machining, when we started building machine tools back in the late 1800s, back in this, I guess, I don't know when the first machine tool was built. That would be good trivia for me, right? Knowing what CNC means, it's also good trivia for you guys. What it means is computer-controlled machine tools, right? The numeric part is because before we had computers controlling the machine tools, we had numbers controlling the machine tools. It was really kind of always computers. But they had NC machines. Yeah, they started building NC machines back in the 1940s, late 1940s. They actually built the first NC machine tool at MIT Lincoln Labs, just east of here, in order to make what? Anybody know? Anybody want to guess? Yeah. Nope. No, it was not a NASA thing. It was not for space flight. So it was like 1947 they built it. I think 1947 is the year, somewhere in that range. They built the first NC machine tool in order to make airfoil shapes for helicopter wings. Now, the wing on a helicopter is the bit that spins around, right? And so what happened with a helicopter, so out at the tip of the helicopter rotor, How fast is that going? Right? So what is that equation again? The speed at the tip of the rotor? It's actually important to machining. How fast is the tip going? How do you know? What are the variables you have to plug into the equation? So you need to know the radius or the diameter. I'll call it diameter. Right? You need to know the diameter of the helicopter rotor as it spins around a circle. What else do you have to know? Yeah. The angular velocity. So we could put omega, right? That's what we usually use for angular velocity. How about if instead of omega, we say RPM? It's just going to make the math easier later. So if we know the revolutions per minute, if we know the speed of rotation, and we want to know the speed of the tip, what's the formula? You guys know this. It's like 7th grade math. Yeah? Pi times diameter. So what's pi times diameter? Circumference. So pi times diameter is circumference times revolutions per minute. And so what are the units for circumference? Meters, feet, inches, right? So if it's in feet, so feet times revolutions per minute, what are the units? Is it really feet though? Is the units here feet? The length of the diameter is feet. What happened? Yeah, go ahead. It's feet per revolution. Right? It's the number of feet that happen every revolution. Feet per revolution. Revolutions go away, right? And we get, so we could get feet per minute for the speed of the tip of the helicopter rotor, right? Why might this be important in machining?
If you're machining with a drill bit and you're going through material, and the speed or the surface speed is different depending on where you are referencing the drill bit to the piece.
So if I'm machining, so you said a drill bit, but it really doesn't matter what type of cutting tool it is, right? So if I'm machining with a tool, the speed of the edge of the tool as it goes through the workpiece material, that speed is pi times diameter times RPM. Is that true? If I've got a drill bit, the drill bit's spinning, we can do pi times diameter, we can multiply it by RPM, and depending on the units we use here, we may have to divide or multiply by 12. So typically with the drill bit, we talk about inches. Typically with this kind of speed, we talk about feet per minute if we're using the US system. So we may have to, how do you change inches to feet? This is a 12 factor, right? Does 12 go on the top of the equation or the bottom? I never remember. Every single time I figure it out because I know I can figure it out. I don't know if I can remember. Right, but we can convert because it's 12 inches per foot, and then you can put that in the equation. You cross off the units. Okay, so the speed of the cutting edge of the drill on the outside diameter is pi times diameter times RPM. What's the speed in the center of the drill? 0. That's going to be important later. Okay, so today we're talking about CNC machining. We're talking about CNC machining. All right, so what I want to do, stop the sharing. So I can stop the share and go here. That's not the one I want. How do I mute that one? That's not the one I want. Almost. How about if I mute? This is how I do it. There, got it. Just have to be smarter than the software. Okay. CNC machining. All right, so we know that pi times diameter is going to be important. Okay. So the CNC part, the computer numeric part, that's how we're getting the information to the machine tool to tell it where to go. If you don't have CNC, you can do it by turning handles. You can do it Etch-a-Sketch style. What's the machining part? Anybody? Who's ever run a CNC machine tool or run any kind of machine tool before they got to M1800? Okay, so what's machining?
Actually, material.
So it's removing material. So in machining, wrong button. Come on, wrong button. Machining is a material removal process. So here, I can draw it on this side. So we've got a cutting tool. We've got a chip. Chip's moving that way. Workpiece material's moving that way. This is my workpiece. Right, so this is the tool. So the tool's moving that way through the workpiece material. The workpiece material is moving that way past the cutting tool, right? Same picture that's on the thing. So this chip flows off. Somewhere in this area here, this stops being workpiece material and starts being chip. Okay, so it's just like when you're taking that knife and carving the piece of wood. It's just like when you're, you ever have a really hard stick of butter and you really want to put butter on your toast? Right, so when the butter's soft, it really doesn't matter how you move the knife through the butter, right? You slosh it through the butter, you slather on the butter on top of your toast. When the butter's really hard, kind of the easiest way is to scrape the knife across the top of the stick of butter. Really annoys me to open up the fridge and find sticks of butter with like a dish cut out of the top because people bring the knife across the top. Really bugs me. I don't know why. Which means I leave the butter out on the counter to get warm. And my wife puts it away and she doesn't know that I'm leaving it out so that I can have toast later. And it's a problem. Anyway, that same mechanism of skiving the butter off the top of the stick of butter is how the metal gets cut when you're doing a machining operation. Same mechanism. The tool moves through, separates workpiece material into workpiece material and chip. Okay? That's machining. We call this large chip formation machining. How big are the chips? You guys have done this, right? You did it in the lab. How big are the chips? They're pretty small, right? Right? Some of them could be really, really thin, talking about thousandths of an inch thick, maybe tenths of thousandths of an inch thick, these chips. That's large chip formation. Could you imagine what machining by small chip formation might be? So you've done turning in a lathe, you've done milling on a milling machine. What do you think machining by small chip formation is? Grinding and sanding, so abrasive operations. Exact same physics at the chip level. The grinding or so you've used sandpaper? You've roughed some up and you see the little fine, little tiny chips that the sandpaper makes? So it's the same exact physics, except there are a lot of little grits of sand on the page. So there's a lot of little cutting tools making little tiny chips as you do this small chip formation stuff. So it's a material removal process, large chip formation. Typically, it's turning and milling. What's the difference between turning and milling? Anybody know? Yeah. So it's whether or not the tool or the workpiece is rotating. So in a turning operation, the workpiece rotates. The tool then moves in and out. Let's see, turning operation. This one, yeah, this one's good. All right. All right, so here's my round piece of material. It's spinning like this, okay? So we're aligned with the axis of the board. The workpiece is spinning like this. We'll have a cutting tool down here. So it's different from this diagram, right? This diagram here, where you see the angle here, we're looking down this edge. So our eyeball is here. Can I draw an eyeball? Maybe. Not really. Does that look like an eyeball? Looks like a fish. Maybe like a pony from My Little Pony. All right, we're gonna get rid of the eyeball. You can imagine that I drew an eyeball there, and the eyeball is focused looking right down this axis, that line of the tool edge, to make this diagram here. So that point right there is that line going through there, okay? Workpiece is rotating this way. So we've got, this chalk really sucks. Rotation. I don't know why we put the units for rotation as RPM, because really the math would be so much easier if we wrote rev. Anytime you see RPM, know that it means revolutions per minute, okay? Because I'm going to write RPM, I don't know, habit. Rotating this way. The tool, all right, so the tool is feeding. The tool is feeding along in this direction. And the chip is forming right here and flowing out, coming off the workpiece. That's a turning operation. So CNC machining, and the CNC part just means you're telling the tool what to do and you're telling the spindle how to rotate with a computer. That's all the CNC part does. The rest of it is all the same. All right, so some things to remember. That axis right there is the Z-axis. The axis about which the part spins is the Z-axis. It always is. This direction, in and out, is the X-axis. So smaller X makes the diameter of the part smaller. Bigger X makes the diameter of the part bigger. Hey, that's kind of intuitive. They did not do that on accident in choosing signs. Okay. What would Y-axis be? In and out of the board. Typically, a lathe does not have a Y-axis. Standard lathe does not have a Y-axis. We do have a lathe at WPI that has a Y-axis because it doesn't just have turning tools that can bolt on its turret. It also has milling tools that can bolt on the turret. So it's a mill turn machine, so we can do both types of operations. But in a standard turning operation, you ignore the Y-axis because you can't adjust it. You can't do anything to it. All right, so this is turning. The workpiece rotates. The tool moves in the X-axis or the Z-axis. Or sorry, the X-axis or the Z-axis. Okay? What do you use to, what kind of parts do you make with this operation? At least axisymmetric, right? So you guys have used like CAD software and draw stuff, right? And the revolve feature, you like make an outline and you revolve the outline and go around the part. Parts that are made with that revolve feature often can be cut on a lathe because it's the same thing except we're taking the material away instead of adding the material when we do the revolve. Okay, and of course, you could have a drill. It broke again. I don't know if I'm drawing the spirals right, but you could have a drill. The drill could make a hole in the end. You could have a cutting tool that looks like this. Part's rotating, it might point the other way. And that cutting tool could go into the hole and you can make an inside diameter, you can make an outside diameter, and you can make holes through the end. And then unless you have a really fancy lathe that has a y-axis and milling tools, that's pretty much all you're going to do in a turning operation. Yeah.
So, like, when you say turning operation, like the lathe is just one of those. Are there like tools that? So, like in the lab, we made a thing that was basically completely cylindrical, symmetrically.
Yep.
Could you make something that like you vise it in like that has a square base, or is that like too unstable on the rotation?
No, so the question is, can you cut a square part in a lathe? Is that the roughly, or a prismatic part in the lathe?
Yeah, because I expect to know.
So you can. You can, as long as you can hold it, but you're going to spin the part, so the features that you make in the lathe will be axisymmetric. So you can, and often, especially in experimentation, so I don't know if you guys know, but the materials science program at WPI is housed in the same building where the machine shops are. And so they do a lot of stuff. So who's heard of this new technology came out in the 1980s called 3D printing? Few of you have heard this, right? Who's heard of the fact that now we do 3D printing with metal very often? And we would love to be able to make like airplane parts out of it. SpaceX uses it to make parts for the nozzles for their engines and stuff like that, right? We would really love to be able to do that. The problem with 3D printed metal parts is we've been machining parts with like CNC machining or manual machining. We've been doing that for a long time. We've been digging ore up out of the ground, refining it, smashing it into the shape, forging it into the shape we want since the Bronze Age. We've been doing that for a long time. We have a good understanding of how those materials behave in extended use, right? Who's ever broken a paperclip by bending it back and forth, right? That is caused by fatigue. The fatigue is caused by work hardening when you bend that paperclip back and forth. That's predictable. We know how it's going to happen. We know how to build airplane wings out of paperclips, although we probably would choose some other material, but we know how to. Problem with 3D printed materials is nobody knows how they're going to handle fatigue, especially. The fatigue cracks and stuff, if you've done stress and strain, if you've studied this, you'll note that fatigue cracks initiate on surface features. So very fine scale roughness on the surface causes those cracks to start. Once they start, they explode. Wings fall off airplanes. That's a bad thing. So a lot of the research that's happening right now, a lot of the research that's happening here at WPI right now is 3D printing metal parts, cutting them up, and breaking them. So very often when we cut these up, we cut them into the rectangles first, or cylindrical, no, prismatic, like stretched out squares, long rectangles, shoe boxes. But the fatigue testers want round parts. So we make them square because it's easy to make them square with like a bandsaw or something. We cut them up into pieces, put them in a lathe, and make them round. So yeah, you can put square parts in a lathe, and you don't have to be using a lathe to do turning. It's a turning operation if you're spinning the workpiece. I have been known in my garage to put the workpiece in the chuck of my battery-powered drill and spin the workpiece using the chuck, the motor of my battery-powered drill, and maybe putting some sandpaper on it to reduce the diameter of the shaft just a little bit as I'm spinning it. It's a turning operation. I'm doing it with, I'm not using a lathe. You can actually mount the workpiece in the spindle of a milling machine, mount the turning tool in the vise in the milling machine, spin the spindle, move it up and down. That's our Z-axis motion. Move it sideways. That's our X-axis motion. You can do turning in a milling machine. I've seen it happen many times. So turning operation is when the workpiece turns and the tool moves in X and Z.
Does that mean that turning pottery on a pottery wheel is a turning operation?
Same idea. Yeah. I mean, I don't think, the potters call it turning, right? Pretty sure.
In terms of plain English.
Yeah, people call it turning. It's the same, but it's the same physics. You're moving the tools in and out. I mean, it's different physics because you're molding or shaping. It's more like forging. It's more like spin forging than it is turning in this sense, because when we talk about turning in this sense, we're usually talking about chip formation. So making parts with chip formation, but yes. All right, so that's turning. What's milling? I think we started this with what's the difference between turning and milling, right? So we've got a good understanding of turning. So the main difference between turning and milling is in turning the workpiece rotates. In milling, the tool rotates. That's the difference. You rotate the tool, so you have a turning, typically there's one cutting edge at a time interacting with a workpiece. In milling, you may have multiple cutting edges interacting with the workpiece. So you have a milling tool. So if you're looking at it from the side here, you see these cutting flutes, these edges that go up. And you've seen it in the machine tool, right? The edges on that cutting tool. And so you can count those number of edges. We call those flutes. Flute, F-L-U-T-E, I think. I really can't spell. Cutting flutes, they're also called teeth. Cutting flutes, teeth, cutting edges. All those terms get used interchangeably. It all means the same thing. It's the number of cutting edges. You could have multiple cutting edges engaged with the workpiece at one time. So how fast? So the flutes engage with the workpiece out here on the edge, right? How fast is the edge of the cutting tool moving as it moves through the workpiece material? So right here, there's our edge of our cutting tool. It's moving through the workpiece material with this tool motion, this velocity. So how fast is it moving through the workpiece material? Same as a helicopter blade, right? In fact, I suppose you could cut, not often, probably not repeatedly, but you could definitely do machining with a helicopter rotor, right? Tends to damage the tool more than you want to, and the helicopter tends to not stay in the air afterwards. But you could totally do machining with a helicopter rotor. But, so it's pi times diameter times RPM, where this is feet, or sorry, this is inches per revolution usually. Because we don't have big diameters. We don't talk about how, it's a 3-foot wide tool, right? How big were the tools you used in the lab so far? Anybody know what the biggest one was? Used a 3-inch face mill in the lab. And you also used, but the biggest end mill that's shaped like this was probably a 1/2 inch that you used in the lab. So inches per revolution, we count those in inches. RPM, revolutions per minute. The problem is this velocity that we talk about here, the velocity of the cutting edge moving through the workpiece material, we almost always talk about that in feet per minute. So 12 inches per feet. That doesn't work, right? Because then it's inches squared over feet. And so I need to do 1/12. And then the feet come out on top, the inches go away. See, that's how I figure it out every time. I never remember if the 12 goes on the top or the bottom. Most people would write this like this. That's defective chalk, right? It's not me. Maybe it is me. I'm the one pushing on it. All right. Pi times diameter. All right, so spinning tool. What kind of parts can I make with this? So axisymmetric parts on the lathe in a turning operation, milling operation. What kind of parts can I make? So you can make anything you can see from the top, right? So you can very easily make any shape that you can see from the top with a milling machine. You mentioned you could do a second operation. If you want to make features on the side of the part, you could flip the part on its other side, and now you can see it from the top again, right? You can attach the part to another axis in the machine tool that does this. So then you could machine on the top and these two sides, right? This side and this side. You can attach the part to another set of axes on the machine tool that do this and this. Then you can machine 5 sides of the part in one setup, right? You can't very easily machine the side you're holding on to in that same setup. You would need to flip it over if you need to put features on that side. But so there's 3-axis milling where the tool's moving. So the tool's rotating, right? The cutting that happens, the chip formation that happens because the tool's rotating. The feeding goes in the X direction, in the Y direction, and the Z direction. It is relative motion between the tool and the workpiece, right? So I could move, so in the milling machines that you guys used, the tool moves up and down, right? It's attached to the spindle rides up and down. And then the workpiece was attached to a vise when he did it, and the workpiece table moves X and Y, right? Does it matter which one moves? It's just relative motion between the cutting edge of the tool or the tool and the workpiece, right? Okay, so it doesn't matter which one's moving. We have in Washburn 108, we actually have a gantry mill where it spins, it goes up and down, and it moves in X and Y, and the vise is fixed, it doesn't move. Not quite true. It's got a rotary table in it, and you could machine on one part while you're putting a part in the vise on the other side of the table and then flip around. So it's a production machine that allows you to be changing parts while you're machining a part. That's kind of cool too. All right. All right, so you can make prismatic parts. You can easily make anything you can see from the top down. We often call it 2+ axis machining if we're moving up and down but not intending to cut, and then cutting when we move sideways. So we're making contour around the outside of the part, making a pocket on the inside of the part. I mean, we violate that when we drill a hole because we are intending to cut when we're moving down. These tools, if you look at the bottom of the tool, so that would be an example of the bottom of a 3. One of these is wrong. There, now it doesn't look stupid. That was the one that was wrong. That's the one I didn't erase, huh? If you're looking at the bottom of it, you've got a cutting edge here, cutting edge here, cutting edge here. So this would be a 3 flute, and then you'll see a spiral that goes up the side from each of these. What's the function of the spiral? Why not just have it go straight? Yeah, the spiral is like a little pump. It's pumping the chips up out of the hole. So the purpose of the spiral is to evacuate the chips up out of the hole. The purpose of the edge, the sharp edge there that wraps around that spiral, is to cut material when it moves sideways through the workpiece. So what's the speed here? Pi times diameter times RPM divided by 12. Right? That's the surface speed here. What's the surface speed here? 0. How do you cut with 0 relative motion? Yeah. But if you're feeding that tool down, will it go into the material? Yeah. But at the center, it's not cutting. It's sort of smushing the material out of the way, nudging it, pushing it. It's not a very efficient process. It tends to make the tool break. It makes the forces go way up in the machine. What do you think happens if the forces go up too high? Same thing that happens if I use this chalk on the board, right? Tool breaks. Forces go up too high. We're going to spend a whole week talking about forces and power and stuff like that. So we're not going to worry about that too much today. All right, so CNC machining, use computers to control it. What's the value in using computers to control it?
Much more complicated things than
You can do very complicated things. So the reason they invented the first CNC machine tool was to make complicated airfoil shapes, because out at the tip of the rotor of the helicopter, it's moving close to the speed of sound. It's the first time we'd ever moved close to the speed of sound. When you move close to the speed of sound, the forces change, a bunch of things happen. Yeah. Took us till what, the 1700s to make a steam engine. Actually going from steam engine to helicopter in 150 years, that's pretty amazing. Right? If you think about it. And then since then, what do we got? We got people building spaceships, flying into space. That's pretty cool. I don't know. All because we have CNC machining. So why do we study CNC machining in this class?
Because we realize how important it is and we don't get caught up in conspiracy.
See, that's the dream answer. Because we realize how important it is. So this piece of chalk, did we have to do CNC machining to make this piece of chalk? Did we do CNC machining to make this piece of chalk? I guarantee that the mold that this chalk was molded in was cut with a CNC machine. My shoes, right? Stitched leather. Any CNC machining involved in making my shoes? So it was the leather pieces were die cut first. The dies were made on a CNC machine. The needles for the stitching were made on a CNC machine. The machine that made the thread, because the thread's wound, the components of that machine were made with a CNC machine. There's nothing that we use today that's more than, I usually say 2 steps. Nothing including the food you eat every day, nothing is more than 2 steps away from a CNC machine tool, with the exception of the few things that are 3 steps away. Most of it's 2 steps away. So you could trace the manufacturing process history. So that's why I say CNC machining is important. Is 3D printing important? Absolutely. 3D printing is very important because it lets us make near net shaped parts, which we can then CNC machine to make the finished part out of. So most 3D printed parts are not, most metal 3D printed parts that are actually used in production are not simply 3D printed. They're 3D printed and then finished machined. I do have an exception in my pocket. My titanium beer bottle opener did not require finished machining, although I probably machined it a little bit by opening bottles with it. So not all 3D printed parts need finished machining. All right, so what time is it? 37. Okay, perfect. We can make prismatic parts with CNC machining. Now, title of the lecture is CNC machining and prototype manufacture. Well, so let's spend the last 5-10 minutes here talking about prototype manufacture. Why is CNC machining important to prototype manufacturing? I remember years ago we were doing a tour in Washburn shops. It was one of the. Did you guys get to go? Because this was the weird 2 years. Did you go on a tour of Washburn shops when you visited WPI to decide whether you were going to come here as a student? Now, if it hadn't been the middle of COVID, you probably would have been invited to walk through Washburn shops if you went on the right tour. The tour groups always come through there. And so I was talking to a tour group, and the father, it's usually the father or the mother that's asking questions like this, because the prospective students are, what's the word? Nerds. And so they're too shy to ask questions, but the parents, even if they used to be nerds, they've gotten over it a little bit. So the father asked, sorry, did I just stereotype you guys? I went here too. I'm a nerd also. It's a term of endearment, right? I saw this great bumper sticker once. It says, be nice to nerds, you'll work for one day. Anyway, so the father asked, do you guys do any rapid prototyping? Now, this was when they were starting to have TED Talks about 3D printing. So I knew he meant 3D printing. I was like, yeah, we do all the time. Because I said, because half an inch deep, half an inch over at 800 inches a minute in aluminum is rapid, right? So we had a machine at the time, we could, with a half inch end mill, we could cut full engagement, half an inch deep, 800 inches a minute. You could put chips in a bucket really fast that way, right? And that's like airplane wing spars are like 98% material removal if you make them out of a billet. So the billet is like the chunk of metal that we cut them out of, right? 98% material removal. It'd be nice if we could 3D print just the material we wanted and then maybe clean it up with a machine tool. Even better if we didn't have to clean it up, right? So you betcha 3D printing is a critical technology, and knowing more about it and learning how to do it better is critical. Can't build a 3D printer without a CNC machine tool today. Sometime in the future, maybe you'll be able to. But today you need a CNC machine tool to build a 3D printer. So this stuff's cool. So we study CNC machining, prototype manufacturing. What's prototype? Yeah. It is often an iteration before the final product. It could be identical to the final product, but what it is we're building the product to find out, does the product do what we intended it to do, right? Does it work the way we wanted it to? Maybe we prototype just a subsystem of a product to make sure that our idea for how so maybe you're making a 6-axis robot, but you want to make sure that your novel way of making the joint for the arm at the elbow is going to work. So you might prototype just that part of it. You could 3D print the prototype. 3D printed prototypes are often very good to see if stuff fits together. So did I make it in such a way that I can assemble it? Plastic 3D printed prototypes are not often good for transmitting loads. Many times the things that we make need to transmit loads, right? I did a project for a company. They wanted to make a product that was, you guys have used like a Keurig coffee maker? So the little plastic cups that you make the Keurig stuff in. They wanted to make a product similar to that shape, basically. We're copying that shape. But they wanted it to be made out of aluminum. It was going to be to dispense something in some like fancy shower head or something. I don't remember what it was for. But they wanted to be able to make those, and they wanted to make them in high volume. When you make something like that in high volume, you're going to make it the same way you make soda cans, right? It's going to be some kind of a progressive stamping operation or a spin forming operation like you do when you make soda cans. But they needed 50 of them. The tooling to set that process up to make them with the process they were going to use when they finally had them would have cost $100,000. They needed 50 to see if their product would work and then see if they could raise capital to invest in building the business to sell their product. I never saw it hit the market, so I don't think they got the capital. But we made them 50 prototypes. We turned them on a lathe with 3/1000 of an inch floor thickness at the bottom of the cup, 5/1000 of an inch wall thickness on the sides of the cup. Right? So we turned it on a lathe. That was not the best way to make them in production, but it was the best way to make the prototype. So these things, so you don't always make a prototype with the same technology you're going to use to make the production part, but you do need it to have similar material properties if you're really truly going to do a test. So that's one of the reasons CNC machining is still very important in prototype manufacturing. Those job shops we talked about, those people that do high mix manufacturing, much of their work is prototype parts. So there's actually machine shops that only do prototype work. They make one or two of something, and that's all they ever do all the time. It's always a brand new part coming in. Yeah, so I think it's time, right? I see a bunch of you getting ready. So we got lab today if you're in section 1 at 3 o'clock. There's a video that was rendering on my computer just when I left. I'm going to post that up for you to watch before you come to the lab. People that have lab tomorrow, it's no problem. You got plenty of time to do it. The people that have lab today, especially if you were numbers 1 through 6. So if you were numbers 1 through 6, please make sure you get a chance to watch that video before you come to class. It's 20 minutes long. I will not be offended if you watch it at 2x speed. I watched yesterday's lecture at 2x speed to make notes because I wanted to remember what I told you about the group project before I forgot. There were some words that sounded normal at 2x speed, which means I must have slowed down. I hope to somehow emphasize the point that I was making at that point with that word. But go back and watch the videos at 2x speed. I don't think there's any reason to watch them at normal speed unless you really love the tone of my non-chipmunk voice. But I listen to audiobooks at 2x speed too. So 2x is kind of tough sometimes, but I need to learn how to talk faster because you can totally listen to my videos at 2x speed. All right, thanks a lot. We'll see you guys tomorrow in this room for lecture, and I'll see you in lab today if you're section 3. And if you are at home or not at home, I don't care. I'm going to keep talking. You guys can pack up. So we have, if you go to the using Esprit at WPI, there was a link there, I think, at the very beginning of the class. There was a link that goes to this Nutanix frame, so you can log in and use Esprit remotely. They tell me they have fixed it and it works now. The first day of school, it didn't work, but they say that it works. So now you can use Esprit from anywhere, whether you have a PC or not. If you do have a PC, you can download it onto your PC, and as long as you're connected to the VPN, you can get the license for it. So you don't have to be in the lab to do the Esprit stuff.
Thank you.
Yes.
Use free software, it really works. I just thought it spent like an hour installed.
Yeah, but they fixed it. You weren't supposed to have to install it.
Okay, great.
It was supposed to be installed, and it was supposed to be connected to the license manager. I forwarded your message to the person who's in charge of that, and the day later, he emailed me back and said it was fixed.